I'm Rahul Singh. Currently, I'm working as a pavement design engineer. Now, what does that mean? Any road that is designed in the state of Maryland is designed by a small team of around 20 people, and I work with that team. Uh, so that's what I do. That's my email. If you have any questions related to this talk, any research collaborations, anything at all, feel free to send me an email. Uh, and let's begin with today's talk. So this is going to be a fairly simple. I've tried to keep it from the basics uh, to in-depth as much as I could. So the today's talk is on local calibration of pavement ME performance models in Michigan. Now there are some terms: local calibration, pavement ME, performance models. We'll go through each one of them as we proceed. Uh, Also, I am using multiple screens. If I'm looking here, I'm still looking at you guys. Uh, okay, so let's proceed. Okay, so we'll start with the introduction, objectives. So in introduction, we'll learn a little bit about pavement ME or mechanistic empirical design. I'll spend a little bit time there. The objectives of this study, the background, data for calibration, methodology, results, conclusions, some future scope. And at the end, we'll take questions. However, if any one of you have any questions, please feel free to speak up. I will not be able to see if you raise your hands or anything. So just feel free to speak up. Okay, so let's begin with the introduction. Now, we all know pavements are multi-layered structure. We have the asphalt layer on the top, we have the base, subgrade. The ultimate aim is we need to transfer the wheel load to the soil subgrade. Pavements broadly are two types. We have the flexible pavements and we have the rigid pavements. Now, we have different design methodologies when it comes to pavement design. We have empirical methods which are based on engineering experience or field tests. For example, the AASHTO 93. We have analytical methods which are based on computing critical responses like stresses, strains, displacements, like IRC 37. And then we have the mechanistic empirical design. Mechanistic empirical design, as the name itself suggests, is a combination of mechanistic and empirical design. So what it does is it predicts pavement performance. When I say performance, performance means it will predict the distresses directly. What is the cracking? What is the IRI? What is the rutting? Based on mechanical and empirical models. For example, MEPDG. MEPDG stands for Mechanistic Empirical Pavement Design Guide. Now, from now onwards, we'll only be talking about design methods in the US, Canada, which is AASHTO 93 and MEPDG. Now, coming to AASHTO 93 and why there was a need for mechanistic empirical design. AASHTO 93, or we call it 93, we have other versions also, but the AASHTO method, it historically came from the AASHTO road test, which were conducted in 1950s. It is a very good method still. I would say around 50% plus states are still using the AASHTO design method for their pavement design. But why did we move from AASHTO? Why did we move from empirical design to a mechanistic empirical design? Three reasons. One, uh, when these AASHTO road tests were conducted, they were for a specific geographical location at the exact same location. We had only one asphalt mix type, one PCC, and only one subgrade soil type. Also, the truck traffic volume has changed significantly from that time, which is 1950s to now. So it is the material, the traffic, and the climate have changed. So now we have to move to a mechanistic empirical approach. Now in mechanistic empirical, you have material characterization, axial load spectra, climatic models, uh, which you can incorporate even if they change. Now, if we have to truly represent a mechanistic empirical, this is how we should write it. A small m and a capital E. What does that mean? We still have more empirical than we have mechanistic. Now, coming to the inputs of mechanistic empirical pavement design. Just like any other design, we have some inputs, we have some processing, and then we have some output. Now, what are the inputs? There are three major inputs, just like in any other pavement design. We have the material. In material, we have asphalt, we have unbound materials. I'll not go through each one of the inputs that I have mentioned, and these are not all the inputs. We have even more inputs in this. All these material inputs are taken into models, and what do we get? Cumulative damage accumulation. Then we have the traffic. In traffic, we have ADTT, number of lanes, vehicle class distribution, axle load spectra, etc., which goes into the traffic model. And then the climate. In climate, we have 5 different components: the hourly temperature, humidity, wind speed, precipitation percentage, sunshine. And this climate data goes into something called EICM, which is Enhanced Integrated Climatic Models. All these three combined gives us our distresses, monthly distress prediction. And when I say distress, it means you'll get the cracking, you'll get rutting, you'll get eye ride directly. Uh, Unlike other models, we'll get directly the distresses. Now, you might have a question here. These are too many inputs. What if we do not have those inputs? And for that, MEPDG has something called hierarchical input levels. What does that mean? If you do not have level 1 input, which is you directly go to the lab, test your material, and then you get the results. If you do not have that, you can also go with level 2 inputs, level 3 inputs. Level 1, you get the accurate data. Level 2, you get it from other correlations. Level 3, you can use a representative value. Now, I'll go back one step and show you something here. Uh, in traffic, you'll notice there's something called wheel wander. Now, why I'm emphasizing on this is because the models in mechanistic empirical are so detailed that they even consider wheel wander. Your wheel is not going to be exactly on the wheel path. It is going to wander. It is not going to be exactly there. So that means if you consider your wheel exactly on the wheel path all the time, you're actually exaggerating. You're actually enhancing, magnifying your distress. It will not be as much as you will calculate it. We actually have a mean and standard deviation even for the wheel wander that we have. Okay. Now, when we say distress prediction, what does that mean? That means you directly get damages which you see on the field. For example, for flexible pavements, what are the distresses that we have? We have bottom-up cracking, top-down cracking, total rutting, thermal cracking, and IRI. Similarly, for rigid pavements, what do we have? We have transverse cracking, joint faulting, and IRI. Okay, so this was about the inputs and the outputs, which is the distresses. Now let's go into the model. What happens inside pavement? What happens inside the mechanistic empirical design? So this is what the overall picture of a mechanistic empirical design looks like. This is just like any other design, except we have some models, some functions which are different. We have climate, traffic, and material inputs, and we provide some trial thicknesses. You can give your own trial thicknesses, or if you want, you can let the program choose. You know, it will optimize the thicknesses for you, and that is what our ultimate aim is. These inputs goes inside a pavement ME model. ME is mechanistic empirical here. Now, inside the model, there are two different types of functions. One will be calling it damage function, and the other will be calling it transfer function. First, the damage function comes into picture, and you get mechanical responses. What are mechanical responses? They are stresses, strains, number of cycles to failure, displacement, etc. After you get these, transfer functions convert these to distresses directly. Your cracking, rutting, IRI. Those are your distress predictions. If these distresses are less than your threshold, for example, I want to design my road for not more than 20% cracking. If they are less than that, you're good. That design is acceptable. If not, uh, we change the trial thicknesses and go in again into the loop. Now, coming back to the title of this talk, calibration of pavement ME models. Now, when we say pavement ME models, we mean transfer functions. And this is what a transfer function look like. So this is just an example of bottom up fatigue cracking model in flexible pavements. Do, uh, don't worry about the the equations, and if it looks too complex and all, don't worry about that. Uh, the last function that you see is the transfer function. So we start with the number of cycles to failure. Some of you might be familiar with this equation. You'll see this in IRC 37 also. This is number of cycles to failure. This is the damage model. We calculate damage index using this, which goes into the transfer function, which is the last one. And here we calculate, or here we calculate the actual fatigue cracking. And what are we trying to calibrate? We are trying to find out the coefficient C4, C1, and C2 in the last function. Okay, so now this is the transfer function for bottom-up fatigue cracking model. What does the transfer functions for all the models look like? We have 5 models in flexible and 3 models in rigid pavements. So this is what they look like. If these equations looks confusing to you, don't worry, it confuses me still. So that's fine. Don't worry about the complexity of the models. They are actually fairly simple. If you go step by step, look at how you get the damage and then the transfer function. But these are the equations that we are trying to calibrate, as in we are trying to find out the coefficients of these functions. Okay. Now, the big question is, we have so many complex models in these equations, and we are trying to find out the coefficients for that. Why do we need to find that? Why can we not use the software, run it with whatever the default coefficients are, and get it? The problem is Pavement ME. Okay, sorry, I did not mention this. Pavement ME is a design software, and MEPDG, mechanistic empirical, is a design methodology. They are the same thing. Pavement ME is just a design tool or a software. It's the same thing. It uses MEPDG to calculate distresses. So Pavement ME transfer functions have been nationally calibrated. Now, what is the meaning of nationally calibrated? It has been calibrated for the entire state of United States, mainly using LTPP data. And that is why, because they have been nationally calibrated, every state has its own climatic conditions and construction practices. So what are the consequences? What if we use it for any state without calibrating it? This is what will happen. You'll have the same pavement structure for any type of pavement, whether it is as cold as Alaska or it is as hot as Texas. You will end up over predicting or under predicting pavements. Now we know what is pavement ME, we know what is models. Now what is the meaning of calibration? What are we trying to calibrate? We are trying to calibrate those coefficients, but doing what? We are trying to do a simple process, which is this. We are trying to go to the field, look at the data, as in we go to the field and look at the cracking. And then we go to the Pavement ME software, put in the inputs and predict the cracking. We are just trying to match these two. Whatever we get out of the software, whatever we get out of the Pavement ME should match the cracking that we have on the field. So we are trying to put these points on the line of equality. So I'm not sure if you have already seen what Pavement ME software looks like, and I thought I'll open the software, show you what it looks like. However, unfortunately, the Pavement ME software that I had, the license has expired, but I have managed to get a small video uh, with that. So I'll just play the video. It's a very small video. It will just show you what the Pavement ME software looks like. What are the inputs and all that. Okay. Okay. So this is what the software looks like. You see, they have different design methods like new pavement, others flexible, rigid. You have the construction years. On the right top window, you'll see reliability and your limits that you want to set. Initial IRI values. Now you have three major inputs. First one, let's go with climate. So this is the climate model. You can select a location on the map and you can choose your climate location, your climate data. From there, it will automatically calculate all these values that you see on the top right window, the climate summary. It will calculate the mean annual precipitation, all these things for you once you select the climate data. Now, the next thing is traffic. So I'll just pause here. So this is the impressive thing about mechanistic empirical. They have very, very detailed inputs. Uh, for example, vehicle class distribution, monthly adjustment factor, axles per truck. You'll notice we even have a lateral wander that I just mentioned. Uh, Axle configuration, you even mentioned the dual tire spacing and many other inputs in there. So every month, what is the distribution for different class of vehicles is also an input. Now, the next thing is materials. So you see, uh, air voids, effective binder content. If you go down to the mechanical properties, you will see asphalt binder, level 1 super pave. That is the E star dynamic modulus. That's level 1. You can change it to level 2 or level 3 based on your, based on the data availability that you have. So, so you have asphalt binder, which is the G star dynamic shear modulus. This is the E star dynamic modulus. Indirect tensile strength. All these inputs goes into different models for different distresses. Okay, I'll just skip the video a little bit for, so that's the unbound materials. You select the resilient modulus based on the level of data that you have. You can select gradation, water content, etc. And that's a subgrade. See, the input level is 3. You can select 2 or 1 based on the data that you have. Now, these are some AC layer properties. For example, the AC surface shortwave absorptivity. All these things go into the EICM, the enhanced climatic model. And the last thing is the calibration coefficient. So see all these numbers that you see, this is what we are trying to find. This is what we are trying to calibrate for. Okay, I'll close this video and let's go back to our presentation. Okay, perfect. Okay, so coming back to objectives now, what are the objectives of this study? One, calibrate the pavement ME models using Michigan Department of Transportation pavement management system data. So basically it is Michigan specific data. Implement different calibration methodologies to calibrate and validate pavement ME models. I'll discuss about the different methodologies that we are talking about here and what is the impact of calibration on pavement design. When we say impact, it means whether our pavements are getting thicker if we use this or are they getting thinner. What are the critical distresses? Are pavements failing in bottom-up cracking? Are they failing in thermal cracking? That is what the impact of calibration mean here. Okay, so now I'll just give you a little bit of background about the use of pavement ME in the United States. So these charts that you see are implementation of pavement ME for flexible and rigid pavements. So you'll see around 18 states are either using it or are using it with some other software for flexible, and around 21 states are using it for rigid. Now, this is the thing. A lot of states have calibration attempts, but the problem is they are not able to use it. And that is because of data. They do the calibration, they cannot use it because the data that they are using is not good enough. Either it's not sufficient, is not well filtered to have a calibration which is usable. Calibration itself is not a difficult thing to do. It's about data. Garbage in is garbage out. So that's the thing. We spent a lot of time filtering our data, looking at the data so that we have a good calibration. If you look at this table, you don't have to look at all the numbers and all the things. But if you look at the data, you'll see that this is the calibration effort for the Michigan. We have the maximum number of sections compared to other states for rigid as well as flexible sections. We have around 163, 121. Now this is new and rehabilitation. I'll only show the results and other things for new flexible sections, not rehab, not asphalt concrete overlays and all that. No. Now If you want to read in detail about different calibration efforts and all that, we have a paper in ASC which is mentioned here. You can go ahead and look at that paper if you want to read in depth what are the different calibration models, what are the challenges, what different states have done, and those things. Okay, now let's go to the data for calibration. Now, data for calibration here means two different things. One, performance data. Performance data means you go to the field, you look at the cracking, and you record it. That's your performance data. The other data is pavement ME inputs, your material inputs, your traffic, climate, etc. I'll be mainly talking about performance data here. How did we get the performance data? How did we filter it, etc. Let's go ahead with that. Data for calibration. So these are the 5 steps that we use to get the performance data and make sure that we are using the correct performance data. We start with the data extraction and conversion. So MDOT here is Michigan Department of Transportation, records performance data for every 0.1 mile. Some distresses may not have the same compatible units as pavement ME. For example, some distresses might be in length in feet, but pavement ME gives the output in percentage. We have to convert them. Next, we make sure we visualize the data and see that it is practical. It does not have extreme outliers. After we do that, we select projects based on a well-defined criteria and statistical requirements. We do have a requirement for minimum number of sections. You cannot have you can have a calibration with 5 sections, but it's not practical. Performance categorization. We select sections to represent all MDOT sections. You cannot just take all the good sections and do the calibration. No, it should be a uniform bunch. And last, data filtering. You smoothen the data for time series trends and filter out any anomalies, outliers, especially based on if you have any maintenance activities, etc. If you want to read in depth about the process of calibration, you can read this was in 2024. You can read this paper of use of PMS data for PMED model calibration. Now, let's look at each one of them one by one. First step, data extraction and conversion. This little snapshot that you see is what the raw data looks like. We got these Excel files, it's actually CSV files, with 200, 300,000 number of rows, where each row is 0.1 mile of data. So you see this TC, which is transverse cracking, is recorded in occurrences, 3 occurrences of transverse cracking. We have to convert that in pavement ME compatible units. We wrote hundreds of lines of MATLAB codes to convert this data into our usable format. Next thing, we look at the data just like this to see if it makes sense, if it has extreme outliers. For example, this calibration study that I'm showing here is from 2023, and that was in PMED version 2.6. The cutoff for thermal cracking was 2,112 feet per mile. That was based on the assumption that you cannot have a thermal cracking spacing more than 30 feet. If you choose data more than this number, you're just skewing the data because pavement ME is not going to predict that. We need to remove such numbers. Other example is joint faulting in rigid pavements. You cannot have number of faults more than 36. Why? Because if you do the calculation for 0.1 mile, you cannot have more than 36 joints. You cannot have more than 36 joints, you cannot have more than 36 faults. We need to remove those outliers or filter the data. After we do that, this is what the data for every single section looks like. So we had like 400 plus flexible sections and 200 plus rigid sections. We looked at each one of them like this. You look at the trends, look at the construction history. If the magnitude is good enough, if we have a good trend, etc. So this is just an example of a flexible section that we selected in our calibration. And this is just an example of a rigid section that we did not select in the calibration effort. Now, performance categorization. Once you have all your sections, you need to make sure that they truly represent the entire overall roads in the state of Michigan. For that, we categorize each section in terms of it is good performing, fair performing, or poor performing based on its trend. And we plot such plots. So The top two plots are transverse cracking in rigid pavements for the sections that we selected and the entire MDOT sections for rigid database. You'll see that we had 72% good performance sections in our selected, and overall in MDOT database we have around 78%. So we did select a representative sections or representative data from the overall MDOT trends. The bottom up is for IRI, flexible pavements. Once we have that, last step is data filtering. So the right plot that you see is the final data that we are using for calibration. Now, we have different types of pavements in Michigan. I'll not go into the details of each one of them, but we have different types of flexible pavements, rigid pavements. This talk is only about reconstruct or new flexible and rigid pavements. These are the number of sections that we selected, the threshold values that we have for each performance model. Again, performance models mean the distresses, bottom-up cracking, top-down cracking, etc. The important thing to note here is this. The number of sections that was required for calibration, that is based on statistics. Statistically, we need a certain number of sections to have a certain accuracy of calibration. And this is the number of sections that we used. And for most of the models, we got more number of sections that was required. Okay. Another input in pavement ME calibration is initial IRI. I'll not go into the details of this, but initial IRI is the IRI at the time of construction. Most of the time we do not have it. We used back calculation, not back calculation as we understand in context of falling weight deflectometer and that. No, back calculation based on the performance trends to get initial IRI. If you want to read more about what is initial IRI, how do we get it in when we do not have the data, you can read our paper, which is on the backcasting initial IRI for surface roughness model calibration for Michigan. Now, this was all about performance data. What about pavement ME input data, which is layer materials, traffic, climate? The materials, layer materials or material properties, which is asphalt, concrete, unbound materials, we got it from construction records, material testing. If the data was unavailable, we use representative values. Now, we did talk about hierarchical levels. Pavement ME allows different level of data. For layer materials, we used all levels, 1, 2, and 3, whatever was available. For traffic, we use level 2. So in Michigan, we have certain traffic clusters. So for each road, if you want to get the traffic, you can use those clusters to estimate what will be the traffic. And for climate, we used MDOT specific NAR climatic files. So MDOT had a research project in the past where they calibrated these NAR specific for their conditions. So overall, hierarchical levels, layer material, we have all levels. Traffic level 2, climate we have level 1, and performance data we have level 1 because it is actual performance data on the field. If you want to read more about the effect of climate on the performance and how did we come up with NAR climatic files for this calibration effort, you can read our study for the impact of calibration, the impact of climatic data sources on pavement performance prediction. So this was all about data used for calibration. Let's come to the next step, which is methodology. We need to make sure that we are using the right methodology. Now, this is the overview of the calibration methodology that we used. We have the performance data, we have the input data for pavement ME. Now, what we do, there are two different ways. One, we can run it outside of pavement ME, which means uh, we run pavement ME on global model, which is default models. We take out the mechanical responses, which is coming from the mechanical models or the damage functions. We use those and then we predict performance outside of pavement ME, as in we used MATLAB codes to predict that performance. The benefit is we have the control now. We can use any technique, we can use any method, we can use any resampling technique. The other one is there are certain models which cannot be done outside. For that, we used Pavement ME. You rerun Pavement ME again and again. Or the other way is recently Pavement ME also has a CAT tool, calibration assistance tool. You can just rerun Pavement ME instead of doing it manually. You can just rerun it on the tool. It is an online based tool. So we use two different methods, which is the least square, which you may be familiar with, and something called maximum likelihood estimation. We'll go through this in the next slides. What is maximum likelihood estimation? For approach one, where we are doing it outside in MATLAB codes, we had four different resampling techniques: no sampling, split sampling, bootstrapping, and repeated split sampling. For the approach two, we just had least square and only no sampling on this. There was no resampling in these techniques. Okay, so these are the models that we saw previously. For flexible pavement, we have 5 different models. For rigid, we have 3 different ones. These are the 5 models for which we used MLE, which is maximum likelihood estimation, and least square we were able to do it for all models. In this presentation, we are only going to discuss these 5 models because we had the results for both MLE and least squares. We'll also have kind of a comparison. These are the 4 different resampling techniques that I mentioned. No sampling, you take the entire data set. Split sampling, you split the data set into 70-30 for calibration and for validation. Bootstrapping, you resample the data again and again. We use 1000 number of bootstrap. And repeated split sampling, you split the data into 70-30 and do that same thing again and again for 1000 resamples. Now, before doing this maximum likelihood estimation on the actual measured data and the calibration process, we did a small thing before doing that, which is we calibrated using synthetic data also. We generated our own data and then see if it works. The benefit with synthetic data is you can generate your own data. You can have any type of error you want to introduce in your data. That's why we use synthetic data as well as observed data. Synthetic data we only use for 2 models, which is bottom-up cracking and transverse cracking in rigid pavements. The idea behind this was maximum likelihood estimation is popular in optimizing non-normally distributed functions. And we already know that bottom-up cracking and transverse cracking are not normally distributed. I'll show you what they look like in a plot. Okay, now let's start with the synthetic data calibration. Before going to the actual observed data, let's go to the synthetic data and see. So we generated data uh, in MATLAB and we introduced certain errors in that. We introduced no error and 50% uniformly distributed random error. And this is what the data looks like. On the left, we have data with no error. On the right, we have data with 50% random error. And this is transverse cracking in rigid pavements. And we tried to fit different distributions in that. I'll cover this in detail in maximum likelihood estimation in the next slides. So what we are trying to do here is we are trying to fit a data to a distribution. Okay. Now, the question is, why are we trying to do it? We already know how to do optimization. Just take a data, try to find out the error between the measured and predicted and try to minimize the error. And that's what we do. And that is what we call least square method. We take the data, we fit a line between that, and we try to minimize the error, which gives us the least square fit. It works most of the time. But if you have an outlier, the data, the prediction is pulled towards this data. So you will expect your fit to be something like this. However, because of this outlier, your least square fit will look something like this. This is something which is beneficial if you go to maximum likelihood estimation. Now, I'll take a few minutes to explain what this is. Maximum likelihood estimation, it simply tries to maximize the likelihood of your data fitting a certain distribution. Now, it looks like a very complicated formula and all, but it is not that complicated. It's actually a very basic fundamental probability thing, probability concept. I'll explain what this is. Also, if you're wondering how did I create this, uh, plot that you see at the bottom, this is a simple GIF that I created in MATLAB, which shows what maximum likelihood actually does. Now, to explain this, I'll take a very simple example of independent events. You toss a coin twice, or you toss 2 coins at the same time. The probability of getting a head and a tail is probability of head multiplied by probability of tail. 1 by 2 multiplied by 1 by 2, that's 1 by 4. Because they are independent events. The same goes with our data. Our data points are independent. Our performance is independent of each other. So what is the probability that one data point in my performance will follow a distribution? At the same time, the second data point will also follow that distribution. It's the same thing. Probability of x1 given theta. So theta are the parameters of any distribution. So x1 given theta multiplied by x2 given theta, and so on. Now, this is what we call likelihood. Likelihood is nothing but multiplication of the individual probabilities. In this case, it will be PDF, which we call probability density function, because this is not a discrete distribution. This is a continuous distribution. From the likelihood, we have to go to log likelihood. Why? Because our computers cannot work with a lot of decimal places. So taking log can solve that issue. We take the log of this, and now our products become sums. So now it is summation of certain things instead of product. We take a negative of this log. Why negative? Because we are trying to maximize the likelihood. If we take a negative, now we are trying to reduce the negative log likelihood. If we take a negative, that becomes negative log likelihood. So basically what we are trying to do is we are trying to fit the distribution with the data. And at that time, the likelihood will be the maximum when it exactly fits the data. What is the benefit? The benefit is it is not prone to outliers. Why? Because the probability of an outlier fitting this data will be very low. So it is not going to be prone to outliers. Okay. So this is what the data will look like. Least square with error without any outlier will be similar to an MLE, maximum likelihood estimate fit. They'll be similar to each other. However, if you have an outlier, this is what your expected fit will look like. This is what your least square fit will look like. And if you use MLE, this is what your MLE fit will look like. Okay. Now, this is the local calibration process. We take the MDOT database inputs, the measured distress, we try to compare it with the predicted distress. Where are we getting the predicted distress from? After we put all the inputs that we got into the Pavement ME software, we get the predicted distress. We are trying to match them. If they are comparable, good. If they are not, we change the model coefficients and try to predict the distresses again. Now, how are we comparing? How do we know if measured and predicted are equal? We use some statistical measures, which are standard error of estimate, bias, negative log likelihood, AIC and BIC values. So I'll focus more on the standard error of estimate and bias values because these are the recommended ones in the local calibration process. What is the meaning of standard error and estimate and bias? So if you look at these plots, you'll see the top left one is high bias, high standard error. That means points are scattered within themselves and they are also away from the center, which they are supposed to be. If you look at the second one, it is around the center but scattered. That means it has a high standard error but not bias. If you look at the third one, which is this, it does not have a large standard error, but it does have a bias. It is away from the center, but they are closer to each other. And the fourth one is the ideal case. It does not have a bias. It does not have a standard error. The last thing in the methodology is design reliability. You may remember the Ashton 93 equation. It's a very big equation which is of the form of a normal distribution, and you have the Z component. Similarly, that is how the design reliability in Pavement ME also works. Uh, so in simple layman terms, 90% reliability means you make 100 pavements from this model, 90 of them will not fail, 10 of them may fail. How do we calculate it? We calculate the average predicted cracking. In this example, this is just an example of cracking. So we take average predicted distress and the standard deviation of measured distress. We create a fit between that. And from here, we get the standard error. Now you have the predicted cracking is equal to, we always predict at 50% reliability and add a certain component, which is a normally distributed component, to add the reliability into your final number. So for example, if 50% reliability last step after we do all the calibration is, what is the impact on calibration? So impact here means, uh, number one, what is the effect on pavement thicknesses? Number two, what are the critical distresses? It was failing in which particular distresses. Was it bottom-up cracking, IRI, rutting? So that is the impact of calibration. We took 44 new pavement section for flexible, 44 new pavement section for rigid, used the calibrated model and designed it using ASHTO as well as the new calibrated models in Pavement ME, and found out what is the difference and also the critical design distresses. Okay, now let's look at the results. So I'll show you the good results first, and then I'll show you some results which are not so good. Between
Dr.
flex,
Rahul,
yeah, go ahead.
I think the screen got unshared right now.
Oh, is it? Uh,
Yeah,
was it for how many
just
slides did I miss?
just just the last one, just the last step.
Okay. I'll share the screen again. Okay, can you see my screen?
Yeah, it's now
Okay,
visible.
perfect. Okay, so let's go with the results. So we have flexible models and rigid models. For this uh, talk, I'll only show the results for rigid model, which is transverse cracking and IRI, not joint faulting, because joint faulting we did it only using least squares, not using MLE. So just the two model. Also, the purpose is to show if MLE works on non-normally distributed data, and we know that our data is non-normally distributed, especially for cracking. Let's go ahead with some of the results. Starting with the synthetic data that we generated for transverse cracking. If you watch closely, you'll see that these black circles are the measured data points. This red dotted line is the MLE fit, and this blue is the least square. Similarly, if you see with the one with 50% random error, you'll see that MLE is slightly closer. Now, how do I know that? Based on numbers? If you look at the standard error and bias, the MLE, standard error and bias, are consistently lower than the least squares. The same is shown in the residuals, where we have a narrower residuals. Residual is basically the difference between predicted and measured. So you'll see we have a narrower residual for MLE compared to least squares. Now let's go with the observed data. When I say observed data, it means actual data, not synthetic data. If you look at these two, which is transverse cracking and IRI, you will see that transverse cracking does not look like a normal distribution. IRI is not an ideal normal distribution, but it is close to one. So transverse cracking is definitely not normally distributed. IRI is close to a normal distribution. Now, before I dive into the observed data, a very important question, which is the question that we started with. Why don't we use the global models? This is why we do not use the global models. If you look at the one on the left, which is global model, means the default calibration values without calibration. This is what your predicted versus measured fit looks like. If you look at the local model, which is calibrated model, this is what it looks like. There's a huge difference between standard error and bias in almost all the models. So basically, we cannot directly use global models. You have to calibrate them for local conditions. Now let's dive into the results for observed data or measured data for transverse cracking and IRI. So if you look at the transverse cracking, you'll see that MLE, these points are slightly closer. Now, why do we have so many points there? This is because of the resampling. We did resampling at the same data point again and again, which is bootstrapping and repeated splits. I mean, that's why you see a lot of data points. So every time we do the calibration, that point is not predicted at that exact spot. It may be somewhere, up or down. And that's how you see that it is not much affected by outliers. If you look at the standard error and bias, you'll see that standard error and bias for maximum likelihood estimation is lower than least squares. And this is the distribution of standard error, bias, and coefficients. You can see that even especially for the bias is lower than the least square method. Now, if you want to look into the details of uh, what is maximum likelihood, how do we derive those equations and all that, you can read our paper on the rigid calibration, and we have one paper on the flexible calibration also using maximum likelihood and least squares. Now coming to the IRI, you can see that they are more or less comparable, least square versus MLE. That is because IRI is close to a normal distribution, and the same is reflected in the standard error and bias values also. This is the distribution of the coefficients, standard error, and bias. Sorry, I failed to mention, why do we have a distribution of standard and bias? There should be just one standard error and one bias values. That is because we are resampling. When you resample, standard and bias every time you do it. So the distribution shows that they are comparable between MLE and least square for IRI, which is a close to normal distribution data. This is the overall summary of rigid and flexible models. I'll not go into the details of standard and bias. We already mentioned that. But overall, for non-normally distributed data, it works good. For normally or close to normal distribution data, they are comparable. After we do the calibration, the next part was what is the impact of calibration on pavement design. So in numbers, if we compute the design layer thicknesses, we are talking about asphalt, concrete and JPCP thicknesses, were reduced by 0.22 inches and 0.44 inches for flexible and rigid sections compared to the ASH 293 designs. If you look at on a line of equality between Astro 93 and Pavement ME designs, you can see they're more or less close to the line of equality. However, Pavement ME is slightly thinner. Next thing, what are the critical distresses? At what distresses are they failing? So for flexible, the critical ones are bottom-up cracking and thermal cracking. For rigid, it is mainly IRI followed by transverse cracking. Okay. Last part, conclusions. First, which is a very obvious conclusion, calibration significantly improves the performance predictions. The global models cannot be used for distance prediction. We have to locally calibrate it. Second, bottom-up cracking in flexible and transverse cracking rigid are non-normally distributed. Total rutting in flexible and IRI, both flexible and rigid are close to normal distribution. That is why bottom-up cracking and transverse cracking using maximum likelihood estimation is a good strategy. MLE outperformed the least square method for non-normally distributed data. For data close to normal distribution, MLE and least square results are comparable. In fact, in some cases, least square works just fine, better than MLE. Pavement designs using new calibrated models are slightly thinner than ASH 293, although I would still say they are almost comparable. And for flexible, bottom-up cracking and thermal cracking are the critical distresses. For rigid, we have IRI and joint faulting. Future scope. Future scope for this study, MLE can be implemented to calibrate other pavement ME models. We have not done all of them. This methodology can be validated using synthetic data for different pavement ME transfer functions. Further studies can be conducted to estimate the impact of different calibration methods on pavement design. And the last one, which is I think is very important, which is even if we are doing it for a state, we are doing the same thing that is same as national calibration. We are pooling all the data into one and then doing the calibration. If you have more data, just like we did, we can have a mix specific, region specific calibration. In fact, we can have something like a simple ANN, which can predict based on different pavement thicknesses, materials, climate, and those things. Now, references, I used a lot of references in this. However, I have only mentioned 4 of them, which I think are very important. And you I mean as the people in the audience, you can go through these if you want to understand calibration, mechanistic empirical design and maximum likelihood estimation. So the first one is the guide for local calibration 2010. I think there is a revised version in 2015 also. Parameter estimation for power law distributions by maximum likelihood methods. This is a very simple paper to understand what are the advantages and how do we do the maximum likelihood estimation. The third one is this is the final report of the project, a part of the project that I just mentioned. Not because we did it, but I'll still say that this is one of the best calibration studies that you'll find with maximum data, a lot of in-depth filtering of the data. And the last one is guide for mechanistic empirical design for new and rehabilitated structures. So this is the entire guide. You can find this online also. It has different chapters. You can find this online to know what is empirical designs, what are the models that go behind this and those. So that is the end of the presentation. Thank you so much. And if you want to check out any other studies that I authored or I did in the past, I have done or I'm interested in parameter estimation, sensitivity, WIM sensors, material characterization, pavement management, distress index. We have done some studies based on that also. So I would encourage you, if you want, you can go check out those studies. And if you have any questions, feel free to send me an email. Thank you so much. And if you have any questions, please feel free to speak up. Thank you.
That was nice presentation, sir. Thank you, sir. Now the forum is open for discussion.
I think Professor Samson Matthew had joined from the further discussion. Samson sir, are you available?
Yeah. Thank you, Rahul. Congratulations for a wonderful presentation, Mr. Thompson. I'm attending
Thank you so
from
much, sir.
NITC in Fairness. Gautam informed about your background yesterday. It was a good presentation and a good you are happy. I'm very happy that you wanted to share that lesson of the research output to the community. It will be very wonderful. I have only one point. Maybe I have to attend another meeting from now onwards. One point, whether how difficult the data collection and what is the procedure they are following to get that, because you are using like a large scale but not like a data. Now, what is that the frequency of data collection? How you are collecting that one, and how it is? What is the data sharing policy that according to your experience, how it is proceed?
Okay, so that is a very good question, sir. I'm just not sure if you're talking about the performance data or the input, but I'll answer both. So every biannually,
Both. I
okay,
just
okay,
wanted to know both. Okay.
okay. So biannually, that is every 2 years, MDOT sends out a vehicle to collect cracking data and sensor data. Cracking data is collected through photographs. We take photographs, and then there are softwares that run behind and see what is the length of the crack and all that. And from there, we get the cracking data. Sensor data works for joint faulting, rutting, and IRI. So there are two different vehicles that Michigan Department of Transportation sends. So every biannually, that data is collected. How difficult it is to collect the data? No, it is not very difficult to get the performance data right now. As in, when I say now, means in 2025. Those are very sophisticated equipments, and we already have some software that run behind them using image processing. So that's not inputs, which is the pavement ME inputs. What is the material, the layer thicknesses, traffic? These are very difficult to get, especially for pavements which have been there for 15 years. Uh, because a lot of that data is 15, 20, 30 years old. We don't have records for them even. So that data is very difficult. For sometimes we even have to core, take out the sample, see what are the layer thicknesses, take it to the lab, do the testing, and find out certain parameters. So performance data, not very difficult, collected every 2 years. Input data, there's no frequency as such. And that is a little more difficult. So when we looked at this data, we had thousands and thousands of pages of plans. You go to the plan and look at what was the design thickness that they used at that time. And then you find some design thicknesses. And then you look at another plan, and it's a different design thickness. Now you don't know. You cannot core every single 400 pavements and find out what the data is. And that is why even more than new pavement, uh, the rehabilitated pavements are even more difficult to calibrate, because we don't know, because some of them are even 30, 40 years old. We don't know what's underneath. So I hope that answers your question, sir.
Yeah. Thank you, Rahul. Thank you, Rahul. Thank you once again for giving a wonderful presentation. All the
Thank you
best.
so much. Thank you.
Thank you, Praveen.
Okay, thank you, sir.
Okay, I see a question in the chat. Oh, let me see. Okay, so I'll read out the question for everyone. Someone has asked, thank you, good morning, thank you for the excellent presentation. I have one question regarding how moisture related problems, particularly stripping, can be incorporated into MEPDG local calibration process. This is especially important for regions that experience extreme climates. Very good question. And I have partial answer to that question. I do not have the complete answer to that question. Uh, First thing, the enhanced integrated climatic model that I just mentioned. There are a lot more things that I wanted to mention about pavement ME and mechanistic empirical design. I couldn't because of the limitation of time. This is what it does. It calculates for fault layers uh, the modulus value at different temperatures. At the same time, it calculates the moisture content at different times of the year for unbound layers. So the strength of your unbound layer is not the same throughout the year. It changes and it incorporates that. Not just that, it also keeps into account the depth at which this is changing. And that's why we have precipitation and other things that goes into this. Uh, that's first thing. Second thing is moisture content in itself is an input to your unbound material. However, the sensitivity of moisture content to the final prediction is questionable. When I say questionable means it actually doesn't vary much even if you change the moisture content, because practically it doesn't change much except if it is rainfall or snowy or something. Uh, in regions like Michigan, which is extremely cold, the minimum temperature that Michigan experiences minus 30 degrees Celsius. That time the water freezes. That is where we have some issues. So to recap the answer to your question, one, it calculates the moisture content at every depth and every month of the year. And second, you can put the moisture content as an input in the unbound layer itself. I hope that answers your question. So if you look at the output of the resilient modulus of the unbound layer is not a single number. It is actually like a wave. It goes up and down. It even reaches like 400,000 psi. I mean, I'm more used to like psi. So it reaches like 400, 500,000 psi, which is as high as concrete, asphalt concrete, in extreme winters or cold temperatures. I have another question. I'll read it for the audience. It says, considering the advanced ME design and detailed calibration practices followed in the USA, to what extent are Pavement able to achieve or exceed their design life in actual field condition? Okay, that's a very good question. I would add one point to this. One, Pavement ME is very advanced. You cannot, I mean, so this is like uh, the inputs that goes into Pavement ME and the models. There is an ANN which works in the top-down cracking model. We have fracture mechanics which goes into the model, very, very detailed. However, if Pavement ME is the best design methodology, that's questionable. I'll not say it's not true, but it's questionable. A lot of researchers still believe that we should go more into empirical than Pavement ME. Now, coming back to your question, to what extent it exceeds their design life in actual field condition? Uh, I would say around 40-50% of the times it exceeds the design life. And that is not just because of the Pavement ME, but because we have regular maintenance rehab in the United States. For example, right now I'm working in the Pavement and Geotechnical Division with Maryland Department of Transportation. We always touch every single pavement in at least, if not more, 6-7 years. There's no pavement which is ideal for 10 years. We always do something, crack sealing, microsurfacing. We do something. So it exceeds the design life in most of the cases. More than, I'll say, 50% of the times it does exceed. Not entirely because of Pavement ME, but also because of the repair rehab that we do regularly. Uh, there's one more question. Yeah, so there is a very famous, not no, it's not very famous, but there is a very interesting quote that someone in some other presentation told me about the Pavement ME. It's just like your supervisors, your advisors' email. You may like it, you may not like it, but you cannot ignore it. It's actually state of the art. It is really good if you look at the models and what they have. A lot of people have worked into it. There's another question. I'll read it for the audience. It is, good morning, sir. It was excellent presentation. As you said, our IRC 37 is analytical method. Can we also adopt MEPDG design? What are your inputs regarding this? Very good question for India. If you want to adopt MEPDG, the short answer is yes, of course we can adopt it. The long answer is the inputs. We do not have performance data. So you're trying to match the performance, as in the actual field condition, to what is predicted by your model or Pavement ME. You need some data which is the performance data. You cannot take one data point, go to the field, measure the bottom-up cracking, and now calibrate it. No, you need at least, if I say based on the literature, 6 years of data. 6 years of data. If you do it every 2 years, which will give you three data points if you do it every 2 years. So you need at least 3 data points to calibrate. Second is the inputs. Getting the inputs, no, it's not easy. You need, even if you use level 3, you need to input some dynamic modulus there. You need to input some shear modulus there. You need to input some indirect tensile strength there. So yes, it can be implemented, and then the traffic data is very detailed. Getting the data would be a challenge, but yes, it can be implemented. The good thing about climatic data, though, is we have NASA data available for anywhere in on the Earth. So climatic data is, we can use it, but other data we need to collect it. That would be a challenge. There is another question. Uh, has any premature distress or failure been observed in pavements designed with the MEPDG in the United States all the time? Yes. So this is the thing. We are dealing with a material which is granular in nature, both asphalt and unbounded. There are thousands of factors that come into play which cannot be modeled. I'll not say which cannot be modeled. Maybe in future we'll be able to model it, but it's very difficult to model. So yes, do they fail? Even if we design with MEPDG, yes, they do fail. Uh, I'll not say that it is very accurate and it will give you what it is. No, yes, it definitely fails. Okay, I think there are new messages. I did not see it. Yeah, I think that's all.
Okay, thank you all. Now I request Sri Shijit PP, Junior Scientist, to propose the vote of thanks.
Dr. Rahul, I think it's just a technical issue. Just a couple of minutes, he's finding it difficult to join. Just a second.
Yeah.
Yeah. Shijit, it's unmute, but it's not audible. Please go ahead, Shijit. It's not audible, Shane. I think both the mics, like Aryo Gold and Shit, your mic is on, but it's not audible. Okay, so in that case, okay, fine. Dr. Rahul, I would like to thank you for giving an enlightenment talk on the topic the local calibration of payment MB performance-based models in Michigan, USA. So it was a enlightening talk where in which he has detailed about the various calibration procedures which was followed in Michigan to do the calibration for the MEPD models in Michigan. And it was a really engaging and enlightening talk. And also the discussion followed, wherein which Dr. Santon Matthew, Professor NIT Quincy, and former director had also joined. I would like to thank all the division heads, our director in charge, Dr. Sudhir KP, and various colleagues who has helped in to make this venture a success. So on behalf of all, I'd like to extend heartfelt gratitude to Dr. Rahul for giving us an enlightening talk. We'd like to follow this tradition of legacy of conducting talks in the future also. Thank you all for joining. Thank you, sir. Okay.
Thank you so
Thank you.
much. Thank you.